right. Teams should not make this easy. There's like multiple. Okay. We are now recording. And let's start. All right, here we go. Welcome Whitfield, everyone. Yeah. So, scale representations from globes down to balls, down to ball posters and digital maps. It's how we show our world in a model to try to help other people understand what is going on. And we're going to look at all of that. And we're going to look at Rock. It's an app that is out there. And I'm sure most of you may have already downloaded it. It's run by the guy out there in Madison, Wisconsin, at the University of Madison, Wisconsin. It's pretty cool. I mean, it works across the country in a lot of international places. So we'll take a quick look at that. So, but things are not always as they appear. My parents to see us at that age. So, well, we all know that. Nice time. How many times have you picked up that one rock in the middle of your field area and you said, "Oh, you're not supposed to be here," and it throws everything off. I threw it there. Oh, are you ready to go? This is my boat. It's fairly new, and it does have the Gulf of Mexico on it. I was wondering, I didn't know how to, I know it was a foot diameter, but I wasn't really quite sure how to figure out the scale. And I should have looked. It's right there, 1 to 42 million. Now, by doing that now, we can now scale some other things. So we're going to look outward, and then we'll look a little bit inward at the 3D scale. So that is the moon, which down to, which is right really close to it. And two things my doctor said: do not ride a motorcycle at my age, and do not play pickleball. I don't want to replace your knees. Reaching for a concussion. Something stupid. So that's the moon. It's like 2 point. Yeah. It's up the 2 miles down line. But the moon just be about, at this scale, will be about 30 feet away, which is right there on the table. So that's how far away we are from the moon. So let's go a little further. And that's outside. 2 helpers. We don't know that. So this would be the next up, which is Mars. So Mars is 4,200 miles in diameter, and it scales down to 3.25. It's really nice. And I suppose at this point, it's like, if I were going to throw this to Ellen and say, go long, she'd have to go about a mile away. That's where, how far this is. So it's bringing things into perspective here. Now, this is Pluto. It actually scales down tennis ball here. And it is far enough away, it would have to be residing in State College, 88 miles away. What gets me is, how do you see this here, this smaller thing? And I agree with John Newbaum that Pluto is a planet still. But Neil deGrasse Tyson and Pluto have, they've made up their friends now. So, it's a little closer to home. The satellite landscape, there's a lot of opportunity, a lot of risk. But just to summarize, there are 14,500 active satellites around us, 25,000 pieces of large debris that they're tracking, and like 135 million fragments. And the statistic I read was a small flake of paint flying at 17,500 miles per hour has the impact of a bowling ball. So it will, yeah. And there's something called the Kessler syndrome, where there's a theory that if they start colliding into each other, there's going to be a pinball effect, and everything's breaking up, and we're going to be trapped. There can be so much debris flying around that we just can't get out. So it's a crowded space out there. So we're going a little further out here. The International Space Station, which is 254 miles altitude. Degrees of an inch off the surface. That's not very good. And it's really zipping around. Now, our favorite satellites are the GPS satellites, 12,500 miles. This scale, about 18 inches off the surface. And there are like 31 of them right now. You only need 24 to be operational, but they're in geosynchronous orbit, which means they pass over the same spot twice a day. So their period is 12 hours, where the International Space Station has a period of 90 minutes. Even further out to the geostationary, that's that really long measurement of 2.8 feet. And they're 22,000 miles off. So they're clear out here. Now, these are the ones that communications, satellite TV, my Sirius XM, all that are up here. And they are geostationary, which means they follow the Earth around. And that far out, they see the full disk of the Earth. So you're here and here and here. You've got the whole Earth covered. I covered that geostationary and primarily loose telecommunications and weather. Now, talk about how things are far away, like the moon and Mars. Let's go a little closer here. And that the Earth is actually, it's not round. It's an oblate spheroid. And if you use the right-hand rule of magnetic rotation, if you can never figure out which way this goes, physics, we know where right-hand rule is. Right hand, put it up, right hand, that's north. That's true through the whole universe. Anything that has magnetics follows that right-hand rule of rotation. For north is up, and it goes this way. So naturally yield to grass, I see. So, the pole here, the equatorial difference between the equatorial diameter and the polar diameter is like 26 miles, which seems like a lot. This thing's spinning, but this scale, that's only 9 sheets of paper. This has a little trouble showing that. The other one's Kármán line. The Kármán line is where NASA says it's 50 miles. And a lot of people have said it's like 100 kilometers or 62 miles. Well, Kármán, if you were on Kármán, figure it out. You can only go up so high with a plane, and you go up any higher, there's no air to give you lift, and you're approaching your forward velocity anyway. So you're spinning around. So it's actually the edge of space. And the Blue Origin goes up to 66 miles. So go up, they throw you up in the air, and you float back down, get astronaut wings. So now there's Bill Shatner. This is the edge of space. And then there's the, this is about 20 sheets pocket paper. That's our world. There. Outside of that, it's considered outer space. I think of AI. That's who I think of. He was scary then. Not Babe or now. Or how. So why not just a little bit more here? Our atmosphere. So at sea level, we're at 100%. Up to 13,000 feet or so, it's still breathable, 70% air pressure. The reason why I'm using air pressure is because the concentration of oxygen is still the same. Going up is still 21% as you're going up. When you start losing air pressure, how you breathe, your lungs do not have any muscles. It's your diaphragm pulling down or your ribs pulling out. So you don't have enough air pressure to actually push air in and get it in where it will do its job. We get exchange. That's why you get out of breath. It's low density, and you can't do the oxygen carbon dioxide exchange. When you get to about 18,000 feet to 20,000 feet, you're at a really risk of hypoxia, which is low oxygen. And about 26,000 feet, that's the zone. Above that, you have to have air. Climbing Mount Everest, you have to have air. So, planes fly about 35,000 feet, which is, in your hand up, you just take two pieces of paper and put together. That's how far away, that's how far up they fly on this globe. This is the one. Breathable atmosphere. 13,000 feet, roughly the thickness of sheet paper. If you have one of the old lacquer globes, it's the thickness of the lacquer. So that kind of puts things into perspective. You know, if we're throwing all this stuff up in the air, and it's only like a sheet of paper on this thing. But that really caught me into it. Okay. So this is what I would call a positive scale failure. The smoothness of the globe, all the rugged terrain, the Himalayas, the Rockies, everything kind of disappears into here. If you want to feel the Himalayas, especially Everest, but not Everest, geez. Mount Everest, you should get about 400 to 600 grit sandpaper. Feel that. That's all it is. This, as round and smooth, everything disappears into it. But being here and using that one sheet of paper in breathable atmosphere, that gives you just how fragile the whole world is. That really made me think. So, moving on. Logical assumption. The error of logical assumption. We make conclusions that are logically appealing, but not supported by the data, because our biases believes everything we think is real. And we think this is what it is, but the conclusion sometimes. Pipelines equal fracking. No. Get the facts. I love that post, but that's pipeline. That's a pipeline. That's not fracking. All right. And this is fracking. You know, perhaps it's all in our minds, it's just a little voodoo. So that was, we saw that at the beach. We did one of those here. So it's the International Space Station. You know, they're up there this high off the globe, but they're still subject to 90% of the gravity. You go, well, why are they floating? And Ellen knows this. Does anybody else know why they're floating? They're falling. They're free fall. Absolutely correct. They're going fast enough that gravity's pulling them back, and they're going around. And how do we feel that? We've all felt it on a roller coaster. On the station, you go around the corner, except in Pittsburgh, where you go straight in a ravine, then you go up. Building Pennsylvania, you're going up a hill, and in Connecticut, if you release stream down, you hit that first valley, and you feel your kidneys go down into your shoes. And heading up the other way, as soon as you start to come up, and then your stomach comes up behind your eyeballs, and you're lifting up off your seat, you're free falling. You're launched in the air and you're coming down until you get your butt planted back in the seat. And it's Isaac Newton's battling force, and we've got Newton's first law, you're trying to go that way, and centripetal force is trying to pull you this way. So at a very exact speed of 17,500 miles at their altitude, it just kind of curves their path around. So they're in constant fall, but they never catch up with the bottom of the elevator shaft. Just keep going round and round. So that's, when I looked at this, I said, well, okay, now I understand. And the first people to actually feel weightlessness of gravity was Apollo 8, as they went to the moon and back. I mean, weightlessness of outer space. So now when we covered the science, now there's political science. Let's read this one first. This one. Solid hydrocarbon. Didn't even know what hydrocarbon is. It's hydro. It's not cool. But I have no words for this one. These are the people running our country. So in the 1950s, and somebody wanted to blow up the moon to prove to the Soviets there's such a power. And all the physicists are going, you don't want to do that. So, globe to map. So, a map is we know what a map is. It's a graphic representation of what we interpret in our mind. And it's the purpose, put it down on paper so we can get somebody else to figure out what we're talking about. So it kind of convey the idea. And that map, that's back there, that's the 500,000 map. I don't have a copy. That's pretty sad now. You have to do something about that. But to go from that is basically you go from the physical Earth to a geoid, which is a gravitational shape of the Earth, shaped by the gravity, to an ellipsoid from the gravity projection. That projection onto a flat paper-like thing, and then into the grid that you're talking about. So it goes from here to the geoid, to the ellipsoid, to projection, and then individual projection like UTM. UTM is pretty good. It preserves distance and angles, and we can go off on shapes, but it's what we use with the quad maps. And any measurements that you make on a quad map in UTM or is actually a great circle calculation. Like from here to here, that's all taken into account, so it's flattened out as a straight line. That's where you can make measurements off of. And things to remember are the North American datum. We use three. The NAD 27, which is based on Clark 1866, NAD 83, which you get GRS 80, that's the gravitational one, and WGS 84, which is one used in GPS units. Now, there are differences between NAD 83 and NAD 27, just because how they were made. So you have to be very aware of that in your mapping, especially going from old maps to new maps. But NAD 83 and WGS 84, the ones that the GPS uses, their center of mass is very, very similar. It's only like 7 feet difference from the center of the Earth. So they're essentially identical. Now on your handout, I showed you the difference between NAD 83 and NAD 27 as far as your geographic grid is concerned. It's the grid window actually moves. So Ellen and John are actually standing in the same place. Standing at this, they have the same geographic coordinates. So they're both at exactly the same degrees, minutes, and seconds. Now they are actually 92 feet apart. Because the shift was 86 feet west and 34 down. That's that far. So if you have something in between there and you're looking at an NAD 83 map and an NAD 27 map, it can change from map to map. And this is why this matters, because the error comes in when you try to use a different datum or a different something to keep it put it into your system. The error isn't random, it's just the direction and magnitude. And you don't start with bad data, create it because you have it wrong. And data mismatch, we talked about that. And projection controls how distance shapes are distorted. So no matter what you do, when you go from here to flat, it's going to be distorted in one way or another. And there are thousands of projections. He's trying to protect something. We've seen that in the USGS poster and all this stuff. But you have to know what you're starting with in order to move it to something else. The errors can cascade through. You get one wrong and go through several iterations. You go wrong, and precision will actually mask inaccuracy. When you start exceeding your source accuracy, you get false confidence, at least overinterpretation. So you have this number with all these decimal points after it. You're starting to think all of these are real. And you start going off this way, going off that way. And reprojection, you can reproject it. It's not going to correct anything. In fact, if you take data that you have, if you reproject an NAD 27 map into NAD 83, everything moves, and sometimes it can be wrong. So I'm going to give you a brief history of Digital Map 1. It's based on this poor sad thing behind me. So the survey began using GIS in 1992, and I was at the first Sun workstation. It's me and Lenny, I think he's back somewhere. Lenny. We were sitting beside each other. We both had Unix Sun workstations, and I was working on GIS, and he was trying to talk to the USGS. Oh, I think we had the very first internet connection in the state. They ran it out to us up there at the Event Press building, and had that huge plug. That was before anything. All you got, you type in and it answers you. Oh, I'm talking to a computer in Michigan. Okay. Well, we were done a couple maps in GIS. It was pretty cool. And since this map was the latest coast-to-coast geology map in Pennsylvania, we should make that digital. We got the Mylars. Be easy. It'll be fun, they said. It'll be easy, they said. No, nothing much that. There was no bridge. Just you can go anywhere on here. There's no projection. My friend Scott Hoffman from the USGS, they tried too, and he said, "That's a beautiful work of art, but it wasn't meant to be digital." And he was correct. So it was just, yeah, yeah, not here, not there. Lincoln Heights, very reputable mapping company. They put all the wing sheets together and all this other stuff, but they moved it like this and this and this. So it looks pretty, but they just don't match. So what did we do? Went back to the original source material, which we did the base map projection, we did the scale. Here we go. Scanned all the stuff and georeferenced it correctly because we knew what was there. And then you knew USGS DRGs were coming up, and the quads went from polyphonic phonic projection to UTM projection, the digital ones, because they were so close together. They said, well, UTM is a national thing, so we're just going to go to that. Well, we were wonderful, so that's how we started doing that. And we keep everything to the original 1 to 250 scale, matched to the original, attributed it, listed the source data and the metadata, and map 61, which is those little page size maps. They've got all source material listed, where to find it, who did it, and the augmentation is also listed. We published it in 2001, and now all the augmentations are on PAGeo. So people go, oh, that's great. And they said, there's some map 61 filled in the gaps in the source data that we had, but it was all reconnaissance mapping. It wasn't on the ground. So they took all the sources that you can see listed along the side of here. All the sources that were put together, and it was like a marathon with everybody. And the Middletown Quad, which is where we are sitting, and we're somewhere here. And this was compiled by Tom Berg and Dave McLaughlin. And people say, oh, it's on a 24 quad. It's published at 15-minute scale. So, but it's usable, but this is the things you have to look at. You can't just take it. Accuracy and precision. This is where we get into stuff. Accuracy is how close the measurement is, what you're doing, and it depends on your reference frame, your data and projection. Limited source data and the scale. It cannot improve by reprocessing. The answer is, am I in the right place? That's your answer. Am I getting the right readings? Am I doing this? Precision is how finely measured and reported things are. It's always expressed in digits. It's easily increased by GPS and GIS. We add precision onto the end. It's independent of the truth. And the only thing it answers is how many digits can we show it. So we'll look at this here a little bit. So accuracy, that first set right there, that's a nice tight shot, but it's off target. The next one, now taken as a whole, if you do competency circles around a shot, you're pretty much in the middle. So it's accurate, it's not very precise. And then there's the, now this is really what you want. Nice tight circle, precise and accurate. But then again, it's always the very hairy model. It really doesn't matter. This is my wife's. And if one watch knows what time it is, a man with two is never quite sure. One is more precise, but are they both one more accurate than the other? No, they're getting their data from the same source. The little transducer on your transmission that counts the number of revolutions of your drive wheel. Where is the accuracy here? The tread, exactly. How thick your tread is. It can vary. You brand new tire, you got at least half an inch of rubber or more on each side, and as you wear it down, you'll be going
it will show you a faster speed, faster. But it's not enough to get you out of a speeding ticket.
You've tried.
I can either confirm or deny. So, okay. Now, on the map accuracy on a 1 to 24,000 map, that's the one we all basically live on. The one defined by the USGS, it comes out to 40 feet on the ground, 1/50th of an 1/50th of an inch rule. And for the 250 scale map, this one is the same rules, and it's at 417 feet. And not there. It's present. .5 millimeter mechanical cuts, which I live with all the time. That draws a line 40 feet wide on the ground. And football, there you go, 10 yards, a little more. That's 40 feet on a 7.5 minute map. Now we had to put arrows here. This one, John and Ellen are 40 feet apart outside. And if you want to do it in here, Ellen's standing in the doorway and John is against the back wall. It's 40 feet from that back wall up to here. One thing you have to remember about accuracy on the map is it's a radius, it's not diameter. So the line or the point can be on that line can be 40 feet this way, or it could be 40 feet that way, or an 80-foot diameter circle and still be accurate. Now on the 7.5 minute topo map, road's 40 feet wide, pencil is 45 feet wide. The USGS house, which I love, USGS, they're 40 feet. So when you're looking at that, you're looking at that. And when you're trying to plot this stuff on the map and you're up against the road outside, you may be in the middle of the road on the map. So let's go mapping. How true is that? How true. So this is not too far. Where was that field trip, Gary? Up, this is in Carlisle. This is up Dragon's Gap. Yeah. Up on top was the Hawk Watch. Yeah. Going up that road, that's like 2015, 16, something like that.
Oh, field conference.
The field conference.
Oh, well, yeah, that's probably
Around there. It's really sharp. It's really cool, but I can see it from I can't see it from my liver. If you want to go up and look at it, it's right there. Just be very careful. It's a very used road. So your scale limits constrains how you map this. You're guessing where you are on the map. Your pencil line is 40 feet wide. But this is how we do that. Now, to get to other map scales, the orange, my pointer here. This is 40 feet right here. On a 1 to 24,000. This is on a 1 to 250,000, which is 417 feet. And then that big pretty map in the back is 1 to 500,000. That 5 millimeter, 0.5 millimeter pencil goes here to here, which is 820 feet. So you're drawing a very wide line on that map. Now this is on your handout. GIS adventures where you shouldn't really go. That is I cut out a scrap piece of map 1 at that plot, and that's how big that is in your hand. The one I have on the handout, I try to get that, I cut it, flipped it out, and I tried to get that as close as I could to what it really is. It may be a little off, it depends on my, at least printer and my my glass window light table. See, that's the relationship between the 1 to 1050 geology digital map 1 to a 7.5 minute map. That's what that is like. If you look on there, there's a lot of tight stuff in there. So what I did was I did this before, took the Wormel, I can't say that right, Wormel storage area, which has an atlas op, which is pretty well researched. And it's got some pretty complex geology right there. And I took the map 1 geology and put it on the 7.5 minute and left the line thickness at 250. You can see that covers a lot of sins. We turn it off. See, that's, people take that, wow, this is what it's really like. Look at, you start right in here, we're in here. Look how much that's generalized. So you could be standing in the middle of this over in here going, I'm on the wrong stuff. This is what this is. If what Rock says it is, it's not yet. So that's one of the strengths of GIS. Now, GPS from your smartphone. GPS, it's pretty cool. My smartphone has, still do have a GPS detector. That's why you can use Google Maps, because you follow it. The way these things work is they broadcast their location and their elevation at every 6 seconds, and they all be once. So every 6 seconds, it's like this, how they move. And your phone or the chip will construct. It doesn't work on triangulation. It works on, I can't pronounce this, trilateral distance. And it constructs domes, spheres, and where the spheres connect is where you are. And then your GPS, your phone will convert that into your location. And then it can further go and go into 2 dimensions and like your GIS mapping application. So it's actually a pretty sophisticated system. And when it first went up, during the 90s, they still had the ability to buzz up buzz up the location so you know where you are. But found that, and that's a satellite array I actually picked up on my phone on the parking lot. Things are it actually has your error, 12.4 feet, which means your regular error is 24 feet around. Now, rocked. You have rocked on your phone? You want to try it? Go ahead, turn it on. This was a requirement. It's a mobile application developed by 4 geoscientists and scientifically curious users interested in geology of the surroundings across the United States and regions. This app is designed and maintained by Microstat Research Group at the University of Wisconsin, Madison, an organization supported by NSA. That's my legal thing I have to say. They don't care, so you acknowledge them. Turn it on, and then get to this point where you get the you get to this, you just skip the login, and it should come up to the screen right? My phone, it kind of went down a little bit, so I had to take another screenshot here. And this is an important observation. Now, it gives you the latitude and longitude. It also gives you your error, how far off you may be. But the latitude and longitude are in 4 decimal places. That will come into play. And it's got a lot of neat stuff. I mean, it's got a front in it. You can record anything. It's got paleo, it's got fossils. The only thing it doesn't have, it didn't use our nomenclature. So it's just where we are. In fact, Jerry Jones did it up a few years ago. Jerry Jones had a presentation with somebody that took it out west, and they had a lot of fun with reporting where they were. And I had it over in Europe that worked there. So push right here. The full thing is this map. You should get something like this. And we are right there. It uses map box. It doesn't use Google or Esri, but it's workable. When I was looking at this, I said, that looks familiar. And you can click anywhere on here, and it will tell you, you'll get this screen, it'll tell you what the formation is. So if you click on it, it'll just pull over to there. I'm just like, why does that look so familiar? Yeah. I digitized, I don't want to look something familiar. And the map scale is a 1 to 250. Oh, okay. So you have to keep that in mind. Go a little further. Again, the false accuracy, false precision, false accuracy. Because the rock will come in a little bit here. It's the apparent detail that exceeds the accuracy of the data. You run into this all the time. It's created by excess decimal places. Somebody rejects it. Scale misuse. Looks scientific. And that ain't right. False precision is confidence without justification. My phone can tell me where I am to 6 decimal places. The GIS gives us incredibly precise coordinates. The challenge is knowing when precision stops being meaningful and when the computer is hallucinating. Yeah, you can't recognize that. Thing is, don't let your GPS steer you. That's a question. So now this is the chart line handout. These are geographic coordinates. So 40 degrees latitude, this looks a lot of math work, but 1 decimal degree. You're looking at the budget. This is how the size. 2 decimal degrees. Now, large shopping center, 3,623. Length of a football field, 4 decimal points, these decimal degrees. With size of a house. And that is the limit for your phone. That's why Brock only has 4 decimal places. That's a limit. But it's the size of a house. So when you get down to 5, that's the limit. It's 3.6 or 3.2. 6, that's the 1. You said the 3s. The size of your cell phone on the ground. How many places have you seen 6 decimal places? 6 decimal degree, that's degree places. So now the next one, yeah, decimal seconds. 1 second is 30 yards on a football. 0.1.
How far is it if you're not on a football field?
Is that?
How far is it if you're not on a football field?
I don't know. 100 by 78 feet. Can't you read? So I point that out. 0.1 decimal seconds. 3 yards. 1 decimal is about the size of your foot. So you can, anyway, get down to the place that you can do 2 decimal seconds. That's now the decimal. This was really hard to measure because that thing is only about that big. Trying to get the scale off of it. That's 50 meters. I get back and go back, and I actually had to get my iPad out. And I came up with about 50,000. Where you have 250 geology on being displayed at 50,000. That's way beyond where you should be. Now, can we pick on DEP? No, we'll pick on them anyway. But this, well, actually, this is how gas wells, this was not too far. House was, look, how gas wells are plotted. So, perfect. Now, to be perfectly honest, this well permit was well before DEP, was well before EER, it's way back. This is when there wasn't that much concern about it. This well was drilled in 1959. So, but it's an excellent way to show cascading error. Has anybody ever had to plot these? This one here is actually printed, it's supposed to be printed on 8.5 by 14. One of my jobs when I worked at the wireline company is we would get packages from the state every month of all the well drilling permits. I had to take those and plot them on quad sheets for the company because we know where to go. Now, how you do that? Now, they're only required at that time this is property was to survey the well in on two corners of the property. So that was it. They didn't require a location, nothing. The modern ones, this is the vertical well, and the actual location is right there. All right, surveying where the well is, so you. But how you did it here is barely see it, but that's the Latrobe quad. So you pull out the Latrobe quad. Oh, it's the Latrobe 15-minute quad. That has some excitement. And there's the latitude, there's the longitude. What you would do, take that corner right there and put it on the tick mark defined by these two, this latitude and longitude. And then that's the location of the well. They would lay the plat on the map, find a well, draw a bullseye. So that's how you did. That's how you found that well. That's how they mapped the well for the state. Now, everything was done by hand. Survey, the upper corner, bullseye drawn by hand. And the plat was originally 8.5 by 11. So even if you print this off, I got that off of Edwin. It shrunk. So if you try to do that there, you're way off. In subsequent years, when we went digital, they took this well and they did some positional backplotting. So they converted it to a 7.5-minute Latrobe, and up here at the top, they did offsets from there. So you already got the error from a 15. You already got the error from hand plotting. Now you're going back from 15-minute to 7.5-minute. You're collecting data. Your data is always as good as what? Your worst source. And if you notice, that is in hundreds of feet, 4,000 feet by 7,500 feet. No 25, 30, 50. And everything's done by hand, and then it was converted over from offsets into GIS coordinates. Now, to be fair, it's not DEP's fault. This was all well before everything went on. But it's a really good illustration of cascading error. Now, this was, I pulled this off of their oil and gas finder website. Now, this gets interesting here. They were down to 6 decimal degrees and 4 decimal minutes. That is the size of a pencil eraser. Wood over here would be different. Wood back there would be different. So you've got all this error coming in, and then you add all this precision, and it doesn't. You can't take. You have to take it for what it is. I mean, you can find a spot here, but the well would be over there, way off over here, and it's okay. That's how. But like I said, that's how it all came in. And we have this. This is a 15-minute Mampetitis built in 1946. How are you going to deal with that? When I worked in oil and gas management, I was there at the beginning of the profile well plugging program. In fact, it was just me and the division chief. So trying to plug wells, and it was just trying to find them. You had to go out in the field to actually find them. Trying to look for information. So we're getting down here. GIS, you can place a point or a line very precisely. Also put it in the wrong place. You think you have something, and this is this, but no. Every coordinate is computed in space, but every map is by scale. GIS does not escape the cartography, inheritance, inherit. Precision is how many digits we report. Accuracy is how wide the truth actually is. When precision exceeds the accuracy, the extra digits, they're not wrong, they're just meaningless. I mean, you can't use them. They will, and if you try to use them, they'll scare you off where you don't need to go. The map scale defines the smallest defensible statement we can make about location. Anything smaller than the line width is interpretation. I showed you on there, when your hand out is really wide, if you try to trace down the middle of that, you're interpreting that because that could be anywhere in there. So, projection is not just reshape the earth, it shapes the earth. They have a mismatch, it doesn't announce itself, it just quietly shows up. Downstream, like, how did this happen? GPS produces points with certainty. See that? Plus or minus. GIS often strips that out. What's lost is not noise, it's the context. With GPS plus minus, and you have GIS. You know where that came. And false precision is not a false precision. It's not a software book, it's just a human assumption. When you assume all those numbers mean something. We trust the numbers because they look exact. Okay, even when the map can't support them. It's the error of logical assumption I talked about before. Most responsible GIS work is not adding details, knowing when the detail can't be defended. GIS makes maps more accurate. Doesn't make maps more accurate. Makes more inaccuracies easier to propagate. So you get this wrong, it's going to go down. I can go show you what the wells look like. Question never, can we map? Question is, at what scale does this remain true? Now, every 24,000 scale, every line provides the actual field work was done boots on the ground. Field work wasn't done at that scale, then the map act may be overclaiming its authority. Map 61, they were reconnaissance, they weren't field checked like the atlas that I have in there. So that's why we shrunk it down. Takeaways. Everything we looked at today, GPS datums, projections, scale, points to the same idea. Coordinates are computed with incredible precision. I mean, this has 1,000 more computable capable things that first space capsules have. Coordinates, maps are constrained by how they were made. You can't change the map. You can't make it more accurate using GIS. Scale defines how wide the truth is, and GIS can't make that truth into the earth. more data, projection, original map scale. We don't add noise, just create false confidence. This exercise is feel scientific. We often see the data. GIS hallucinations. That way. See, Ellen liked that. The most responsible GIS work isn't adding detail. It's knowing when the detail stops being true. I mean, I love GIS because you can take anything from any scale and put it together, but you have to know your data source, where it came from, because some of the stuff may be function. So with that, deeply indebted to Ellen, John Newbaum, Jody, kind and helpful assistance. Just remember, be careful out there. That's my fun thing to do. It's no longer fun, or when they tell me, Tom, you're done. So, speaking of which, if you liked the presentation, that's my contact. If you didn't like my presentation, my name is Al Giuseppe.
No, that was very good. If you guys are game, we can stick around for just a little bit more for questions. If not, I have a rant. No. You set me up nicely to.
Where did you?
So I want to talk about PAGO because Tom gave us really good context on where that came from, where the digital files came from. So I just want to point out to you, most of you online, because everyone here knows it, but I'm looking at you right here. So the biggest complaint I get from PAGO is zoom in. So current zoom level exceeds the intended use. And so the biggest complaint I get is, it goes away. I'm trying to do work and it just goes, can you keep it? Like, no, we can't. We can't keep those lines. And Tom perfectly illustrated why. It would be irresponsible of us to keep those lines on the computer screen when we've now exceeded any kind of truth.
And who's to blame?
Because you digitized it?
No, I'm to blame because we originally set that up. I said, don't go past this.
Oh, to do that. Yeah. No, that was a good call.
My name's on that.
Why couldn't you just increase the width of the lines to correspond to the accuracy
So
in that display, for example?
So, yeah, that gets trickier. But actually, so another source of map is a NGMDB map viewer. Those are raster images, so you get exactly that. You just have a paper map that you're zooming in and out. So actually, that holds true for NGMDB map viewer.
What you have to keep in mind is the resolution and the accuracy of the underlying data. I mean, we use enlarging Xerox. The wider, everything gets wider, but so does the data. But can the data support that level of precision? And you see that, I think the third page of the handout, you look at the difference in how wide the geology is and how this is exactly, that's the wide lines. Okay. This is the generalized 250, and this is the 24. And the difference between these two is enough that you may be standing in here and be standing in here when you get this on your phone. Well, why? That's why.
So we have a helpful tip from online, and that is using Rocked while speeding along the turnpike, hoping your position refreshes within the map in real time.
Yes, it does.
Thank you for that.
And your white tails too.
All right, so unless there's a pressing question from the audience, we are going to adjourn and we can hit Tom up for more questions afterwards. So reminder for those of you here, sign in since your PhD credits. PhD. That's been a long time. All right, and I will get the certs out on Monday. Yeah, busy weekend, so it's not out of week. So. All right, so thanks so much. Next month, we have Joe Lee. Yeah. Oh, man, another retired Tom. Yeah, right, yeah, eight. Okay, so next month, I think he's talking about oil and gas wells. I don't read your newsletter.
We have a Facebook page.
Yeah, oh,
No.
and we just started this. There's this new social media trend going around called Facebook. I don't know what it is, but Nicole says it's pretty hopping. So check us out on Facebook.
Everything on it is true.
All right, thanks a lot, and be safe.
Yeah. It was about 15 years ago when Facebook was really,
Really good job.
I